I assume many of you have already attended a bunch of talks in the microservices track of which this is a part. And what I'll be talking about today is some of the problems with respect to performance that arise when you have a microservices architecture, and how you might leverage modern machine learning approaches towards getting a handle on the performance optimization problem. My name is Ramki Ramakrishna. I work with Twitter. I work with the platform engineering team at Twitter. And I'm part of the VM team, the Java Virtual Machine team there. The work that I'm going to be describing today is actually joint with with a bunch of colleagues at Twitter, Joshua Cohen. Jianchao Liu was actually a summer intern who spent last summer working with us. He's a grad student at Purdue. Joshua Cohen is a team member in the Mesos Aurora team at Twitter. Chris Regado is an SRE with the SRE team at Twitter, and Alex Wilchko was with the Advanced Technology Group, which is part of the Twitter machine learning and Cortex teams. And this work wouldn't be possible without the collaboration with colleagues in a bunch of teams at Twitter. With that preamble, let's dive into the problem. Here's a picture of the wheel that you see over here with those little annotations which you can't read along the circumference are all of the microservices that make up Twitter. So when you send out a tweet, and it lands first with the Twitter front end, and then gets routed to a bunch of services which will do various things to either persist that tweet, help it populate timelines of people who are your followers, and so forth. So the effect of that single tweet is, in fact, to orchestrate a whole bunch of other actions which are performed by other microservices that this first service will call upon. And as a result of that, lots of things might happen. And before your tweet actually appears on someone's timeline, there might be a bunch of other services that might need to do their job. For example, the database or the storage layer might need to persist your tweet. The social graph will need to find out who your followers are so that their timelines can be updated with your tweet. Maybe if you being a Twitter user have a lot of follow a lot of people, it might have to do some filtering in order to figure out whether this tweet should appear in your timeline and so forth. Suffice it to say that there are a lot of microservices that together make up the Twitter experience. And to give you some numbers, there's roughly on the order of 1,000 or so microservices running within Twitter. And in terms of the number of service instances, so every service might itself be built of a number of instances, usually horizontally scaled, which will process your requests. And so if you look at all of the service instances for all of the services that are running there, they might be close to 1 million or so service instances running. And you can think of a service instance as a process or maybe a small set of processes. These all run in Twitter's data centers, and the data centers themselves have hardware of varying kinds. So we might be running Intel processors of a certain generation, and then as we upgrade our data center, there might be racks full of new hardware. And so at any one time, there might be instances of a specific service that might be running either on new hardware or older hardware. In addition, there might be software upgrades going on. When you have close to 1 million instances of 1,000 services, and these are being upgraded, weekly or quarterly or whatever, at any time, there might be some instances that are running an older version and some which are running a newer version of the software as upgrades are slowly rolled out. So there might also be situations where your hardware is, your OS is being upgraded. So for example, I might have half of my data center running a version of Linux, and then half of it is being upgraded with a newer version of Linux. In other words, there's lots of change that's always happening in the data center. Moreover, each of these services that are running in the data center might have different performance characteristics. So some might require, if for example they were running Java, some might require a smaller heap, others might require a larger heap. Some might make use of native memory, others might not. And then the services themselves will make use of, for example, the Java platform in different ways. And so there is no one-size-fits-all solution that can be rolled out in a data center of this kind, which is built out of microservices. Here's a picture of a typical or a performance stack at Twitter. In this case, this is a microservice that's written in Java, and so it runs on the JVM. The hardware, it's, let's say, x86 hardware running a Linux kernel. And on top of that, we might be running Mesos containers. So each of the services might be running in its own container, and there might be some amount of resource and cross-container isolation provided by that container framework. Within each container, there might be one or several JVMs. In this case, I show two different containers running on the same hardware, each of which is running a JVM. Now, if you look at this stack, the performance of the microservice, some performance metric, some figure of merit that we care about is shown by the function f. But f itself is parameterized by various tunables, which are provided in the layers beneath. Many of you have used the JVM. You know, for example, that the JVM offers lots of tunable knobs. Those here are shown by the parameters J1, J2, and so on. The microservice itself might provide certain configurable parameters, S1 through S2, and so on. And the settings of these parameters might affect the performance F, which we care about. In addition, the lower layers might have other tunable parameters. And so what I'm trying to show over here is that in order to optimize the performance of the service, there might be a lot of tunables you might be able to play with. And that's the problem that we are trying to solve here. Let's take the example of the JVM. Okay, the hotspot JVM has, close to here. I show something like with this version of Java that I was running, they're close to 757 or close to 800 knobs. Now, not all these knobs actually affect performance. Some of them are to adjust various aspects of behavior, and they may or may not affect the performance of your microservice. But a large fraction of them probably do. And then, depending on the microservice that you're running, some microservices might be sensitive to the performance, to the settings of certain parameters. Others might not be. Some of these parameters might be sensitive to hardware, so they might work well. A certain setting might be preferable on certain hardware, or newer hardware. A certain other setting might be optimal. In addition, the setting of one parameter might affect the optimal setting of a different parameter. In other words, if I tune one knob to get optimal performance, and then I tune another knob, the combination of the two might affect performance. And so there's a lot of mutual interdependency between the parameters. There are some of them which are completely independent, some which are mutually interdependent. With something like 700 parameters, of which, let's say, 400 are tunable, and can affect performance, trying to find an optimal performance point is very difficult. What do we typically do? Typically we looked at blogs, we've looked at postings, we've looked at Oracle release Oracle release notes. People have performance blogs and so on, and we know some parameters are supposed to affect performance quite a bit, and so we hand tune them. Maybe we try to tune a few parameters. We run some test loads, and we find out that, okay, with this setting of parameters, I'm getting good performance. And so I tune those parameters to, and push them out into the data center. First of all, doing this kind of hand tuning is itself time consuming, it's labor intensive, and it's error prone. So it might be the case that I've tested my microservice with a certain load, and in production, it's receiving a different load. And so the parameters that I set in my hand tuning may or may not be optimal in production. With thousands of microservices, what often happens is you look at one, you're writing up a new microservice, and then you look at the parameters that are used by a certain other microservice. That kind of looks like your microservice. But what do? You say, hey, this set of parameters is working well for them. My service is somewhat similar in its shape as the other service, so why don't I just use those parameters? And then I'll run some test loads maybe, and it'll turn out to be a fairly good setting, and so I start using that. And so a lot of parameters that we have that are being used by microservices are cargo culted from settings that were used in some legacy microservices that exist in my data center. So at the time at which I do my performance tuning as a writer of as a developer of the microservice, the settings that I find might be optimal, but as I upgrade my as I make changes to my microservice, I fix bugs and so on, those parameters may no longer remain optimal. Because of the frequent upgrades of all of the layers of the stack, and especially the application, the microservice layer, as well as the JVM layer, which are probably changed much more frequently, as well as the OS layer and the network stack and so on, all of these upgrades make any optimality that we achieve be very transient and fleeting. Within a couple of months of having tuned something, it'll probably be obsolete and no longer be optimal. And so our hypothesis is that many of the microservices that are running in our data center are actually operating below optimality. And optimality here can be defined in different ways. You can think of power consumption, resource usage. You can think of the throughput that the microservice is giving, the number of requests per second it's serving, and so on. You can define your criterion for optimality, and with respect to any of those, at any point in time, a large number of microservices are probably running below optimal setting. So here I'm going to be talking about our attempt to leverage machine learning to try and solve this problem. With thousands of microservices and lots of upgrades going on all the time, and heterogeneity in the hardware and in the software stack, it's very difficult for any team of people to be able to really make a dent in this problem, right? And so how do we leverage machine learning for this? Let's look at performance optimization as a formal optimization problem, okay? So we are looking at a function f, which is whose domain is an n tuple, and a vector of n variables over a domain x. So x is the Cartesian product of wherever x1 through xn range. So they could be real values, they could be integer values, or they could be enums. So each of these parameters, x1 through xn, takes a value from its domain. So for example, I could have, the first one might be a heap setting, and I might have heap settings that go up in units of megabytes or units of 256 megabytes or so on. I might have a garbage collector choice, which might be an enumerated setting, which either picks a parallel GC or a CM or a concurrent mark sweep GC or a garbage one GC. and so on. And then there might be other parameters that will control the behavior of whatever GC that I picked. They could also be things like what compiler JIT do I use, and what are the performance parameters of that compiler, of that JIT. And the optimization problem is to find a configuration, which is a setting of these parameters, such that the objective function f is maximized. So this is a purely mathematical optimization problem. And it turns out that most of, when we talk about performance, there are often a whole bunch of constraints that we place on the performance. We can't, we can't say that, in other words, we can't say, for example, that, oh, you can use a heap of any size, and thus kind of make GC go away forever, because you're using an infinite or a huge heap. So there might be constraints. For example, there might be a constraint which says that the heap size must be below 10 GB. Okay, that might be a constraint that I place. I might place other constraints. For example, x1 and x2 here might represent the size of the young generation and the heap size. And there's a constraint that the heap size, the young generation size must be less than or equal to the heap size. In fact, it should be strictly less than the heap size for any reasonable JVM setting. Or I might have a constraint that says that the tenuring threshold that I use must take a value between 0 and 15, because that's what the JVM gives you. So a setting of 30, for example, doesn't make sense. I might have more complex constraints. For example, I might say something like setting a constraint on behavior. And this here might be a W here in the third bullet over here. Wx is less than k. W might be defined as some sensor reading that comes out of my application. So just like f is a performance metric, W is another performance metric, and I want to optimize f subject to W staying below a certain threshold. So for example, I want to maximize throughput subject to the 99th percentile of my responses being below 5 milliseconds. I might say that every request gets a response, so Rx equals Tx over the time domain over which I'm carrying out my run. So these are the kinds of constraints that we might ask for. In addition to these constraints, which we can actually define in terms of sensor readings that we can take, there might be hidden and uncontrollable variables in the system. So for example, I can't control in a production setting, I can't control the load that's coming on the system, right? It might be that the load varies by time of day, or by the season, or there might be certain spikes in the load. My function might execute on different kinds of hardware, right? And I don't as someone who's deploying the microservice, I might not be able to control which hardware platform it runs on. So this might introduce noise into the function. So if I'm looking at the performance of the microservice, depending on which hardware platform it's running on, it might produce one value for f or a different value for f, even with the same settings of the JVM parameters, right? And if I don't know how to control for hardware, the value of the function f looks like noise to me, because or at least f looks to be a noisy function to me. There might also be inter-container crosstalk. In the picture that I put up, there were two containers that were running on the same piece of hardware, and because of the shared hardware, let's say because of shared network, network buffers or network bandwidth, there might be crosstalk between the containers, and that's something I might not be able to completely control. It could be that the paging cache for the two containers is common, in which case, if one container hogs the paging cache, then the other's performance might be affected. Similarly for disk I/O, for example. So there's inter-container crosstalk that might be present, which I might not be able to control for either. And so all of these will make the optimization problem one of optimizing a noisy objective function f, because hidden variables, hidden parameters appear to be noise. So the performance tuning problem comes down to the following steps, right? First, we have to pick up a performance metric that we are going to optimize. We decide on the knobs that we're going to be tweaking, and then we use an iterative strategy to tune these knobs. That's how a human would typically do it, right? This is what the performance engineer might do. He says, okay, you know what? These are the most important parameters that I've seen affect the performance of my microservice. I'm going to pick those set of parameters to test. I'll pick values for each of those parameters, and I'm going to run my system. And I'll make some measurements of its performance. And then based upon what I saw, I might make some changes to the parameters and look at the performance once again. And depending on whether this, changing one variable or the other is changing the direction in which I'm moving, am I improving performance or am I degrading performance, I might learn something about the shape of the optimization surface, if you will. And based upon that, I might try other parameters. And as a result of that, through some process of iteration, I might actually arrive at what looks like a reasonable set of parameters that optimizes my performance. Now, with an automation assistant, what we are going to do is just basically replace the performance engineer making those changes and instead have a black box tuning assistant. So the black box tuning assistant will be told what set of parameters it can tune. So it knows which knobs to turn, and it knows what the constraints on those knobs are. And based upon those, it'll pick a suggestion, run an experiment, which we'll call an evaluation, get back a value f. So I change x1 through xn, run the system, measure f, check whether the constraints hold or not, and based upon that, I'll say, okay, now I need to look at another performance point. So all of this we want to be done by this black box tuning assistant without human intervention. So how do we do this using machine learning? So in the industrial operations research and industrial engineering literature, global optimization of functions has been studied for a long time, ever since the 60s. Because optimization problems regularly arise in engineering problems. And one of them is called Bayesian optimization. And basically what it is a method to learn potentially noisy cost functions iteratively and efficiently. So basically, the idea is that I should be able to run, to search a huge search space. So let's take an example. Let's say I have 30 parameters that I'm tuning. Each of them can take 30 different values. So the entire search space can be 30 times 30 times 30, 30 times, right? So 30 to the power of 30. That's a huge search space. We can't do an exhaustive search of such a space because our experiments themselves are expensive and they take time to run. And so I need to be able to, through only a small number of probe points, be able to learn the surface and navigate towards an optimum. And that's what Bayesian optimization gives me the ability to do. It can find optima very quickly on a wide variety of response surfaces. They don't need to be monotonic, unimodal, single global optimum. They could be highly nonlinear surfaces, and still it's able to nonlinear, multimodal, and high-dimensional functions, and it's able to find the optimum fairly easily. So here's an example. Let's say we've done 3 experiments, okay, which are shown there by dots. And let's say, for simplicity, we're using a function f, whose value is controlled by one parameter. So this is a function on a single variable. And the variable value is on the x-axis, and the performance is on the y-axis there. And higher performance is better. So we've got these 3 values, and what might we learn from here? Well, we might think that, okay, maybe if I reduce the value of the parameter, maybe I pick -4, it might give me a higher performance because I think probably a parabolic trajectory fits it. But let's say the true function is actually something like this, right? We don't know this. The true function shown here by the dashed line might be the actual performance on a performance surface. And what we've taken is readings of this kind over there. So how is Bayesian optimization going to work on this? What it's going to do is Bayesian optimization essentially models the function as what's called a Gaussian process. So at any point, for any setting of the variable, the value of the function is supposed to be a probability distribution with some mean and some standard deviation. And the mu and the sigma at that point is what the Gaussian process is going to learn as you give it more values. So we start off with this probability distribution whose shape we don't know. It's kind of a very wide probability distribution. All we know is that it's normal. And then as we learn each point, we refine our knowledge of the mu and the sigma for the probability distribution at that point. Okay, so here's our original function, and this is what, after having gotten 3 points, this is what the this is what the Bayesian optimization system thinks the shape is like. So the blue shape defines what the Bayesian optimization system has fitted to the values that you've given it. So having gotten these 3 values, how is it going to pick the next value to evaluate? Because the Bayesian optimization system is actually going to help you search for the optimum. So what is the next point to pick? It doesn't do a random picking of the point. What it does is it'll look at the optimum, the best possible value that we've gotten so far, and then it'll basically take the slice of the probability distribution that lies above it, because those are the things which will improve performance. And what it'll do is at every point, it'll take an integration. Basically, it'll look at the expected improvement. So the improvement times the probability of that improvement. And it'll take an integration across a vertical slice over there. And so for every point, I'll get what's called an expected improvement. And what the next point to probe will be one where I expect the greatest improvement. So in this case, I'll pick the point that is a little bit to the right of -2, probably around -1 or so, because that's where the expected improvement is maximized. So really what we've done is we've taken an unknown function and we've reduced it to optimization of an expected improvement based upon the model that we have, the Gaussian process model that we have. And so the next point that we'll pick is around -1. Oops, let's see. Oh, for some reason that disappeared. But anyway, so we picked that point, the point to the right of -2, and we find that we find what the correct value is. And then we repeat that step. We look at what the expected improvement. Having gotten this the fourth value, basically all of the probability along that point collapses down to the reading that we just took. And so that reshapes our model. And based upon that, we can then look at the next optimal point, which turns out to be between those two. So we read that, and having taken that, the expected improvement over there has vanished, and the search turns to looking at the point to the left at around -3. And so we take a reading at that point, and it turns out that we'll have to take something in between because the model thinks that that's where the optimum is. And so having found the reading at that point, the next iteration of the machine learning algorithm says that, okay, you should look at the point that's between 0 and 2, because that's where expected improvement is maximized. And so we take that, and having read that point, we find that, in fact, it turns out that it's actually reduced performance. So one of the things is that since we don't know anything about the shape of the function, and we're learning it as we go, there might be evaluations we'll do which will look at highly suboptimal points of the performance space. So at this point, basically, I'll kind of go through these quickly, but basically we probe another point, we find this over there, and then finally it turns out that we have one point between 2 and 4, which seems to maximize the expected improvement. We take that, and then through another couple of iterations. Can you hear me? Yeah. No, not at all. All right. Yeah, so through a series of such evaluations of the objective function, we'll find the optimum. So that's how it works in a single dimension. And obviously, as we increase the number of dimensions, the problem becomes more and more difficult in practice for a human to do, because a human could have possibly done this. Let's look at what the Bayesian optimization as a service looks like at Twitter. So what we really want is we have a Bayesian optimization service running as a service, and our performance optimization, our JVM optimization system will make calls to this Bayesian optimization service in the manner in which I described. So this is actually, when building this Bayesian optimization system, which was done by the Cortex team at Twitter, what they wanted was something that would be easy to use. It would require minimal coding by the user, in this case the user being the tuning service. It should support multiple languages, so that depending on which language you're running your microservice or your tuning service in, you could call into the APIs offered by this Bayesian optimization service. And it should be able to run concurrent experiments. So you could run multiple experiments at the same time. So here's what the API looks like. So the scientist is really the one that's running the experiment. The scientist is the experiment set that we create. And we have a name for the service, for whichever service we are tuning, and then we have a way of specifying the set of parameters that we want to tune. And for each of the parameters, we can specify a range. For example, value A may be an integer type that goes from a minimum of 0 to a maximum of 2. Value C might be an integer goes from 0 to 10. Value D might be an enumerated type that takes values red, blue, and green, for example. And then, having set up the experiment, you ask the scientist to make a suggestion, which is the evaluation that we're going to do. And we take that set of parameters, that the job here is the set of parameter settings for value A through value D. And with those parameters having been set, I test my service. And when I test my service, it gives me back a figure of merit, which is the performance objective that we are trying to optimize. And having gotten back that value, having run that experiment, I feed that value back into the machine learning system. So I ask it to update that experiment I'm running with the parameter settings and the value and the throughput that I obtained. And having updated that, I can go back and ask him to provide another suggestion. And so we kind of go through this last 3 lines iteratively until we find a setting that optimizes my system. And this is really how it was built. There's basically an auto-scaling group over there, so that multiple calls into the Bayesian optimization service can run efficiently and scale according to the load on the optimization service itself. There are lots of other approaches towards global optimization, and here we list a few. Random search is an obvious one. Instead of having any intelligence having almost no intelligence in the system, we can still do some kind of spraying, random search in our high-dimensional space, and be able to perhaps look at and find something that's at least better than what I'm running right now. There are various other approaches which divides up, the parson trees one divides up the entire space into basically it does the equivalent of a walk down a hierarchical tree, where settings of certain parameters will divide up the space, and then you'll search within that subspace. And there are lots of other ways of doing this. Reinforcement learning has been used, especially so by Google in their data center cooling, for example. And Bayesian optimization is preferred at Twitter for many of our machine learning and optimization work, because we found it to be robust, extensible, and it's been tested in a large number of applications. And it provides a fairly narrow and elegant API through which we can do the optimization. And here's some of the ways in which it's been used at Twitter. It's been used for spam detection, abuse detection. There are various deep learning applications where we run neural networks, but the neural networks themselves are tuned using the optimization service. So for example, you might pick some parameters in the architecture, the number of layers, for example, the interconnections between the layers, what's the what's the aggregation function that you're using at each layer of the neural network, and so on. And then things like Hadoop cost reduction has used Bayesian optimization to good effect. And I'm going to talk about JVM performance in particular in this talk. And these are some of the sampling of JVM parameters that we used. Last summer we did the summer intern did a project in which he picked a handful of the parameters that we could change. So for example, in this case, I list a few of them. There were some 30 parameters in all that we changed at one time. And just to do a quick recap, we have the service, we have the JVM, we have the kernel, and each of these settings can be changed. In our case, we are changing J1 through Jn and measuring the effect on the service through measuring of some performance metric F. So as I mentioned, there could be other parameters that we could tune, but in the next few slides, what I'm talking about is just the J1 through Jn being changed. But there's no reason why S1 through Sn or K1 through Ko, etc., couldn't themselves be subjected to the same kind of the approach that we are taking could be used at any layer of the stack. So basically, what we did was we took a microservice, it's a large production service, and it's used to access user objects at Twitter. And this was picked because it was a mature service that didn't undergo frequent deploys, which made some of our prototype and proof of concept experiments easier. It ran a large number of service instances, and we'll see in a moment why that is important. And the setup for the proof of concept was basically a microservice staging environment. So we didn't run the experiments directly in production, even though I've been telling you that, in production things are different from staging. We did use real production traffic, which was kind of tapped into the staging cluster. And the reason we did this was because we didn't want the staging cluster to be redeployed very frequently while we were doing our science experiments, if you will. And the performance metric that we optimized was requests per second per unit GC cost. So in some sense, if I increase the requests per second, which increases the throughput, that's a good thing. If I reduce the GC cost, that's a good thing. So in each case, basically the performance would increase if the direction in which the performance metric increases is where the system performs better, basically. And this is how it was set up. Basically, we had the JVM tuning service, which is the one that is going to be orchestrating the system. And there's a certain number of instances of the microservice running in this kind of controlled environment. And what we did was we asked the BaseOpt service is the little pink rectangle at the top right. And we ask it for a suggestion. Okay? And having gotten a suggestion, we generate a JVM configuration based upon that. And we upload the configuration into a file store service. And having done that, we look at all of the baseline platforms running in the system. In my cluster, and basically we want to bootstrap our test system, the evaluation which is running on shard number 0, using the settings that we've just gotten from the Bayesian optimization service. And so we restart that shard and then start measuring performance. But before we do that, we want to make sure that there's a baseline against which we can compare. And that baseline should be running under similar conditions to this one, so that we are actually able to do an apples-to-apples comparison. So having done that, we run the experiment, which is the evaluation for a fixed duration. And each of these instances is actually has a lot of sensors which are logging into the observability and metrics service. And so as the experiment is running, these metrics are being collected in the metrics service. And having run the experiment for a reasonable duration, we then look at the performance metrics that came out of the metrics service and compare it with that of the baseline. And having done that comparison, by taking the ratio of one to the other, we know by how much we improve performance. And that's the suggestion that we then send back. That's the that's the score that we then send back to the Bayesian Optimization Service. That's the value F. And then having gotten that, we then go back and ask the optimization service to send us the next suggestion. And so this here is a trace of the set of the number of iterations we did. This was for 30 parameters. And one over here is the baseline where we performed as well as the original set of settings. And so you can see over here that there's a large number of probes that we do during the performance, while we are trying to learn the shape of the function, which turn out to be suboptimal. But there's a large number of them which actually go and improve the performance quite a bit. And so towards the right over there, around iteration 75 or so, we've actually found a configuration that's about 2x better. So over here, if you look at the way things kind of the values of the performance metric are distributed, you can see that there's a good balance between exploration, which is somewhat like gradient descent methods use, where having found a value and another value which is better, we try to kind of go up a gradient, versus exploration, which is where we go further out from where we are and try to probe good performance points. So based upon that, we finally found that after about 80 iterations, we found something that we are satisfied with, and we go with that. And here's basically what it looks like in terms of the performance ratio plotted over the duration when we ran the experiment. If we look at the requests, if you remember, the performance metric was requests per second over GC cost. If you look at the requests per second, the baseline as well as the evaluation gave you exactly the same number of requests per second. But in terms of the GC cost itself, the GC cost of the optimized instance was much lower than that of the baseline instance, and that's how we ended up improving performance. Here's a quick look at the changes that seem to help. These were basically found by the optimization service without any help from us, and basically it turns out that the new generation size was identical to what had been tuned, what had been hand tuned in the baseline system. It, however, decided that a smaller tenuring threshold and a smaller survivor space sizes were more optimal. It found that you wanted, so in the JVM, there's some prefetches of objects that are done during GC, and it found that the interval for that prefetch had to be larger than the default setting. We also gave it some old generation allocation filter parameters to tune, and it tuned them slightly differently, and it turned out that sped up promotions quite a bit because you were allocating much more efficiently out of the old generation as a result. It said that I should use more GC threads than we had actually been using by default. And then it also said that the compilations, the method sizes which are subject to compilation should be much larger. Actually, this is not compilation size threshold, but inlining size threshold should be larger. So I should be able to inline larger methods into other methods. And the performance gains were, of course, in the GC overhead, and these translated into tail response latency that was much smaller. And in turn, this could translate into lower data center footprint, because for the same load, you might be able to run fewer instances and still be able to serve the same load into the system. So for a smaller data center footprint, you are able to serve the load that you normally get. So the takeaways from the proof of concept were that because of hardware heterogeneity, seasonality in the ambient load, load spikes, things could kind of go awry. Okay. What we did was we took the optimal setting that we had gotten in the staging environment and ran them in production, and we actually found that they didn't run very well. We also found, and I'll come back to this in a little while. We also found that occasionally we'd have very suboptimal suggestions from the Bayesian optimization service. So the microservice that you are tuning should be able to, or at least the architecture should be such that one or two instances, if they perform suboptimally, your entire service shouldn't get taken down. We also found that in order to converge rapidly to an optimum, you need to reduce the noise in the measurements. So there could be noise because of changes in the environment. Platform or hardware heterogeneity could also introduce noise in the manner in which I first described. The sensors might themselves inject some noise into the system. And the amount, if we reduce that noise, we can get convergence faster. And there's a trade-off between the evaluation length. So typically when you have noisy measurements, what you do is you run the evaluation for a longer period of time. But of course, if you run the evaluation for a longer period of time, your convergence is reduced. But what we found that you could do parallel evaluation so that you could run multiple suggestions at the same time and thus be able to converge faster even though you ran evaluations for a longer period of time. And all of these can, of course, affect your convergence speed as well as the quality of the optimum. I think I've probably talked about a bunch of these. What you have to do is, what affects things is the choice of performance objective, the choice of parameters to tune, the duration of the evaluation runs. So if you make very short evaluations, they turn out to be noisy. You have to have sufficiently long evaluation runs. You have to factor out hardware effects because hardware can itself inject noise into the experiment. So you might want to run experiments on different hardware and keep them separate. You have to protect against environmental and sensor noise. You need to use baseline configurations for normalizing evaluation. So if your ambient load is changing and the baseline and the evaluation are subject to the same changes, then by taking a ratio of the two, you can normalize out that noise. Long-range effects are important. In other words, if your experiment is short, you might not be able to see things that develop after a day, for example. And there are various ways of looking at this, and one way is to actually open up the black box and expose new sensors which will look at the direction in which this long-range effect is heading so that you actually have a read of that. And finally, as I said, staging is not production because staging loads are different from production loads. So in order to fix those problems, we ran evaluations on fixed hardware. So each of those was a separate experiment. We ran concurrent evaluations, and then we used production loads, basically. Another thing that we did was we used redline load. So we don't want to be able to be just testing our system with a fixed load. We want to be able to vary the load. And so we have a setup through which we can do ramping redline loads and then look at the cumulative performance over that ramp-up period. And that turns out to be a good way of actually finding an optimum. We want to terminate, obviously, poor suggestions early. And because of the fact that we have a good metrics collection framework, which can be fed back into the experiment, we can monitor how the experiment is going. And if something is suboptimal, we can terminate it quickly. And finally, experiment sets is something that we used, in which what we do is if we have a history of some experiments and we are changing our microservice in some ways and want to find a new optimum, what we can do is make use of the history, and the new experiments will follow a shape that is somewhat similar to the previous shape but different in some details. And so we can leverage the fact that we know the history in order to make the optimization process converge much faster. And the way we've actually, in the implementation that we're working on for this auto-tune service, microservices which are running within the Twitter data center can opt into the auto-tuning. So they can say that, OK, I want my service to be subjected to this auto-tuning. They can place evaluation instances behind a load distributor so that we can be protected against load spikes, which will inject noise and slow down convergence. And then we can control the load profile and the shape of the load, which will be tapped in from production into our evaluation instances. We specify the objective function itself as a query on the metrics. So as we run the experiment, metrics are being collected, and we can run a query which takes a composite of a number of metrics and maps that, the query then evaluates to a actual scalar real valued number, which is our performance function. So you could take a composite of a number of metrics and try and optimize that. And these are all picked by the service which you're trying to optimize. You can also set performance constraints, which will take a SQL query on the performance metrics and yield a Boolean which says whether or not that constraint was satisfied or not. And so basically you're optimizing the objective function as the first SQL query subject to the performance constraints, which is a set of other SQL queries. And then we specify the parameters to tune and their ranges and the duration of the evaluation runs. This is what the implementation actually looks like in practice, and this is basically the prototype that we ran was written in Python. This is being developed in Scala, but basically the shape is somewhat identical. The auto-tune service is out to the right over there. It has its own little storage which stores histories of experiments that are in progress. Remember that an experiment itself might be long running, and experiment sets need to be stored, and so all of that is done in that storage service over there. Once you've reached an optimum and you're happy with the performance, you push the configuration to configuration service so that next time the service starts up, it can pick up these optimal configurations and run with them. And we expect that when the thing is running in production, that services will automatically, services that opt into the service will automatically find their optimum and kind of redeploy at the opportune time with those settings. So the conclusion here is basically that continuous automated optimization is, we knew that it was something that we needed, and it seems as though it is possible using Bayesian optimization to actually make a dent in that problem. And mainly because with a very small number of probes, so in that experiment with 80 probes, 80 evaluations, we found a near optimum in a space that was huge. I mean, it was probably equal to the number of 30 to the power of 30, which is as many as the number of atoms in the universe or something like that. Anyway, a very large number of values. We are able to actually find the optimum fairly easily. And we hope that this automated tuning will actually push the efficiency envelope in our data centers. There's some challenges that remain. One is the dimensionality. In practice, there are thousands of parameters. We picked 30 of them. Tools today are can deal with some number of parameters, but if you increase the number too much, then the efficiency, then basically we have a slowdown. It turns out that some of the algorithms used in Bayesian optimization have cubic complexity, which means that beyond about 50 or 60, you cannot actually you can't simultaneously tune so many of them. And so you need to have some strategy for tuning, say, 1,000 parameters through some kind of iterative, in some iterative way. You have to, of course, deal with noise and non-stationarity, which are things that we are working on. In terms of dimensionality, I should also state that more recently, linear methods have been found that seem to work really well. And so that's something that the Cortex team is working on to try and get these experiments to be more efficient. And that's it. If you have any questions, please feel free. Yes.
I just want to see if I understood this correct. In the case where you say you have 30 parameters, each have 30 values, is it pseudocode basically you pick one of those parameters, you go through Bayes optimization for one of them?
No.
Or you do all different ones, change values all at the same time?
Yes. So let me repeat the question for the recording. The question is, if you have 30 parameters, are you tuning them one at a time? Basically, pick a parameter, find an optimum setting for it, then go to the next parameter, find an optimum setting for it, and so on, stepping through the parameter space. And that is like, going in, along the coordinates and tuning them one at a time. No. So basically, what it does, because there, what it would depend upon is the path through with the sequence in which you followed these parameters would determine the value, the optimal value that you see, which may or may not be a global optimum. So what it actually does is it changes all of them at the same time. And some might change, others might not change. And basically, based upon, you would expect that it would, with 30 parameters, you might expect about 60 different, at least 2 different values for every parameter might need to be checked. And so you would expect that, you would have at least 60 different points. But in practice, no. In practice, it changes all of the parameters at the same time, and it goes all over the place. So they're all being optimized at the same time, if you will.
There was a graph in which you showed that after 80 evaluations, you found that the performance was 2 times as compared to the baseline. So when do we stop
Yes.
this experiment?
Yeah.
Optimal performance will be 3 times as compared to baseline. Do we keep running tests, and does it give an indication that yes, this is the best performance, you cannot go beyond?
Yeah, good question. So the question is, how do we know that we have converged to what may be an optimum? Obviously, we don't know the shape of the performance surface. It's huge. And so the value that I've shown over there, where the performance is 2.1 times more than the baseline, how do we know that's an optimum? We don't really know. It might be 4x, right, as you said. And so basically what we do is we use a convergence criterion that depends upon basically how many iterations have we gone without improving performance. And so you'll have to use heuristics of that kind to figure out that, oh, you've run a long enough experiment, and there is not much improvement that you're seeing. Now, we are trying to expose APIs from the machine learning system, which will allow us to, if you remember, we looked at the expected improvement graph. We can look at the mass within that graph. And if that has shrunk below a certain level, then the tool might be able to tell us that, look, I don't think there's much improvement to be had here, because from what I've learned in the shape of the function, there is very little, the expected improvement is almost non-existent. But obviously, tools can, it all depends upon the way in which we are regressing. We are regressing against a Gaussian process model, and your optimization surface might have sudden dips which you'll not be able to see. There are parameters we can tune of the Gaussian process, in particular in what's called the covariance matrix, which basically tells us how quickly how smooth or how sharp the changes in the system are, and as you change values, and those could be exploited. But right now, there's not an API through which we could actually change that. It runs with a fixed set which it learns over time.
Are there any situations in which human might be able to, make better decisions than machines?
Yeah. So the question is, might humans make better decisions than machines? I think with a small number of parameters, humans might be able to make decisions that are better than machines. But it's a difficult question to answer, because with a small number of parameters, the machine can actually run almost an exhaustive search and find an optimum. So it can do as well as a human. With a large number of parameters, unless the human has deep insights into the shape of the performance surface, the human may not be able to do very well. If the human does have those insights, then they can be used as constraints on the optimization function. And so you expect that at every level, as you're tuning these parameters, you might call upon experts to specify how, what ranges to use for these parameters and so on. And I expect, in fact, that the microservices, the owner of the service owners will actually, or each of the stack owners will actually specify what parameters to tune, what ranges to set. But because the actual settings, which are optimal for some specific application or service, might vary, you don't want a human spending that time. You want the machine to automate that search. And that's really what this gives you. because with 1,000 microservices, there's no way a team of humans can take care of this. Thanks. Any other questions? The question is this available as an open source library? So the machine learning system is not currently open source. It's derived from an open source project that came out of Harvard and University of Toronto called Spearmint. And Spearmint is available as an open source package. And there's actually lots of Bayesian optimization packages that are available in the open source. SIGOPT is one. And you can, so all of them offer interfaces that are somewhat similar to this. So there are black box optimization packages out there which are open source. In terms of the auto-tune service that we are building, my hope is that we'll build it in a sufficiently abstract manner that we can open source at least some part of it so that you can adapt it to your own setting. But obviously, it'll require some amount of specific configuration. So that is indeed our goal. Yeah. Any other questions? All right. Well, thank you very much.